Question 1 asks for us to find the geodesic equations in the Schwarzschild spacetime. So we start with our general geodesic equation here, and starting with our time component, we set mu to t. Due to the symmetry of some of the Christoffel symbols, they will have a multiplying of 2. This is because there's two cases. We have t, tr, and trt here, and that will give us our first geodesic. Our radiogeodesic then has 4 non-vanishing Christoffel symbols. That is then substituted by all their given values in the question. Moving on to our polar geodesic. This one has one symmetry of theta, r theta, and theta, theta, r. And then we have another non-vanishing of theta, phi, phi. Substituting those in, we get 2 over r and minus sine theta, cos theta as our two coefficients. For our azimuthal geodesic, they both have symmetry, that being phi r phi and phi phi r, and phi theta phi and phi phi theta. Those have 2's on them as well, giving us 2 over r and 2 over tan. The relevance of these is that it can help model trajectories in Schwarzschild space-time free-falling projects. So this is essentially how planetary motion is calculated. Moving on to question 3, we're asked to use the radial geodesic. So we've rewritten that back out here in the Christoffel symbols, and we're given some conditions. One is in a circular orbit, therefore r is constant, so its first and second derivative of r should equal to 0. We're then given the plane of theta is equal to pi over 2. That is once again a constant, so d theta, theta's first derivative should be 0. This gives us our new radial geodesic equation of rtt and r phi phi as our only non-vanishing Christoffel symbols left. Substituting those in, we then get sine squared pi over 2 is to be 1. R minus 2gm is on both sides of our equation and therefore can cancel, leaving us with gm over r cubed, dt by d tau squared, and d phi by d tau squared. We need d phi by dt, however, so we can apply the chain rule here. We've used d phi by dt times by d tau times by d tau by dt, and that gives d phi by dt. That gives us our final thing of gm over r cubed is equal to d phi by dt, all squared there. Now looking at the orbital period, we have t is equal to 2 pi over omega. Omega is d phi by dt. Substituting that in and squaring everything, we get t squared is equal to 4 pi squared all over gm r cubed. This follows Kepler's third law of t squared is proportional to r cubed, and therefore we have verified using the radial geodesic conditions.